So today we will be talking about two super awesome topics. So we've got a guest speaker, yes, as we do pretty much every month. So yeah, we have Ehsan Kermani here from Modular. And if you're familiar with the project called Mojo, which is now open source, and the Max runtime, this is an optimized runtime. I'm going to let Ehsan do all the talking there. This is just a quick intro. After he talks about how to build PyTorch custom operations and super optimized PyTorch kernels, then I'm going to talk about dynamic and the adaptive systems and ways to actually route traffic and do congestion aware traffic. And also I added a new section for today's talk for my portion, which will be after Ehsan's, where I'm going to talk about how to use AI to actually improve CUDA kernels and also use it to do adaptive routing and all the like standard stuff. But we're going to dive a little deep into CUDA kernels, how they're built, and then also show how AI has been used by a few companies to actually tune these kernels and get like high performance. So um, my talk is going to be a little bit more about inference. I think, yeah, Ehsan's going to talk more about the PyTorch, yeah, which is also inference related as well. So I think let's do that. And yeah, Ehsan, you said you'll talk for about 30, maybe 45 minutes, and then I'll come in. I'll continue to record at the end if we go over, and feel free to drop whenever you need to. So.
Awesome. Thank you so much for the intro. I'm Ehsan, super happy to be here. I'm so excited to talk about Max and Mojo and the new capability that we recently introduced to bridge PyTorch with our stack. So the agenda today, I'm going to talk maybe for about 10 minutes to set the context about what Modular is, what type of problem we are solving, and why you should care. So the problem in AI software infrastructure and challenges, and also I'm going to talk about the solution from Modular's point of view, which is Max and Mojo. And also I'm going to link to the real impact success stories that we've had so far. And we're going to have a hands-on session on writing custom ops with Max and Mojo, and also live demo in Jupyter that I've provided. Also, all the I have provided links, but everything for this talk is open source. I'll share the link as well. So the main target audience for this talk is, I'm assuming that most of you have worked with PyTorch for inference models. You care about total cost of ownership just beyond NVIDIA GPUs. And you would like to future-proof your AI software. That means whenever another XPU comes in, you want the same code to work on that and not rewrite your own infrastructure or kernels or etc. in that particular piece of software with their own maybe dialects or programming language. Tired of vendor locked in and hardware limitation, and eventually want to basically have to save cost. So at the high level view, Modular mission is to provide an alternative stack for today's AI software, but also in general. It's what we are providing is actually quite profound. Our stack is unique in the sense that we own the compiler, the programming language, the AI framework that's built on top of it, the inference server, the cloud, etc. So all these layers, they have been designed from bottom up in a composable and a comprehensive way. The way that traditional or existing AI software hasn't really been built that way. Can take C++. At the time, there was no maybe GPU when it was being written. But Mojo, for example, has been created by having this sort of heterogeneous architecture in mind. So you can take C++, the alternative will be Mojo. You can take PyTorch, the alternative will be Max. And these two components I'm going to talk today. There are multiple ways to look at these components, but entering with PyTorch, I think, is one thing that most people can relate to. If you would like to know more details about all of these things that I've talked about, there's an extensive blog, Chris Latner, our CEO, has wrote on modular.com, democratizing AI compute. Please do check it out. It should answer a lot of the questions, for example, about what if or why not that system versus this or something like that. Please do check it out. So I've talked a little bit about, the problems, which is vendor locked in, primarily all the AI softwares are being deployed on AMD. The complexity, that means multiple tools, multiple languages that you have to touch if you want to optimize layers, and the performance gaps between these layers. And also all of them, they translate into cost. This diagram is meant to show you more like a study. If we want to, case study, if we want to see, for example, vLLM here, and if we ignore the serving part, if we look deeper, we'll see there is a PyTorch component, there is torch.compile, there is torch inductor, there is Triton. And if you go deeper, you'll see CUDA libraries, AMD libraries, all these things. If we want to compare, again, from bird's eye point of view, if in modular, what you will see is there's Mojo, there's Max. I'm not going to talk about, Mammoth and all the layers after, but Mojo is going to be the replacement for C++. Max is going to be the replacement for all those that I talked about. So everything, if you want to, also try out all of them together. You can definitely do pip install modular. It's as easy as this. You can use UV or any way that you would like to install your Python packages. If you want smaller packages, we have pip install Max, and pip install Mojo is also coming. What is Max? So at a higher level point of view, Max is a modular AI framework. It comes with Mojo. You don't need to install Mojo separately. It has Python Graph API. It has Graph compiler in it. It has inference server, all the optimized GPU kernels that we wrote in Mojo. There's no single line of CUDA here. And all the hardware abstraction that you get out of it. What is Mojo? I'm not going to talk extensively about Mojo, unfortunately. But Mojo is, as I said, is a heterogeneous system programming language. The syntax should be quite familiar. It's Python-like, but it's compiled, it's typed, and it comes with memory safety guarantees such as Rust and with the performance of C++. I'm going to also show you one example of a Mojo code for GPU kernels in the notebook as well. So we briefly talked about TCO, but what TCO means basically is if you pay X dollars for the GPU, how much do you actually gain from it when you deploy a particular software? All of the factors are like there is performance, there is utilization, there is maybe accuracy that a particular type of implementation of a model will give you that doesn't really quite translate maybe with the report that was mentioned in the paper, in the original paper. Also the operational complexity. For example, our container size is around 9 times smaller than vLLM container size. And the reason is we don't have any CUDA. There's no, the only dependency that we need to talk to GPU vendors and XPU vendors is basically driver API. There's no CUDA library, nothing. We have our own, basically. And I've put a sample of these two recent success stories. In Word, we have on average 70% faster on TTS compared to vLLM on recent NVIDIA B200. And also with TensorWave, about 70% max is fast. Max is the fastest inference engine on AMD, also the recent MI 325X. Also, I want to mention that these two, we've put them together because I want to show you that there's no vendor lock-in. Same Mojo kernel works on both GPU. And these are not just marketing claims. They are real-world results that have been verified as well. So now let's get our hands dirty. Now I'm going to actually get to the PyTorch custom app with all the context. If you have deployed a particular GenAI application or a particular GenAI model, let's say, and if you've profiled it and you want to optimize a particular layer, you may have seen how to do it, but roughly what you need to do is in today's world is to write some sort of CUDA kernel. So PyTorch provides a way to write C++ extension. What you need to do is, of course, you need to have that knowledge of writing C++, CUDA kernels. You need to have the build system. You need to provide your Python binding, compile it, debugging the cross-language issues, and all these things. The build tool can be quite complex, but more importantly, the development cycle is slow because you have to touch multiple things. If something goes wrong, everything falls off. On the other hand, MAX and Mojo is quite different. So the API at the high level for Python, if you want to optimize a particular app, what you need to do is use our Max Python API and import your PyTorch, max.pytorch, and wrap your custom operator using Max Python API with graph up. And what it does is our graph compiler takes care of a lot of things, including kernel fusion, memory planning, etc. for you. And if you want to have your own Mojo GPU kernel, what you will need to do is to package it up, and you basically call a single line custom app library to import that Mojo code to your PyTorch application, and you can use it like any regular function. Okay, I think we have time. Okay, now I'm going to show you the live demo. Let me restart everything and run everything from scratch. Okay, so what I'm going to show you is basically all these things that I've told you, but in real code. The example that I have here is I'm loading small GPT-2 type of models for demonstration. So this is a particular model, Diallo GPT medium, that's quite small. It's a transformer architecture. It has 24 GPT-2 blocks. And what I'm going to do is in stage one, I'm going to basically pass a bunch of inputs, all these things, and we're going to do a normal eager mode, PyTorch inference. All these things just to show you, okay, everything is working well. And as the first example is we are going, so if Okay, if we go to the model architecture, we see that, okay, GPT-2 block, it has layer norm, attention, also layer norm, and MLP layer. The first example is, okay, let's go and replace layer norm in PyTorch with max layer norm. So as I showed you, the API is basically to import max and Mojo graph op, and here I'm using ops.layer_norm, which comes in max, and I'm gonna also wrap torch.compile. I'm gonna wrap my custom layer norm with torch.compile to get the benefit of torch.compile memory planning as well. But also one thing to note is that we are doing destination passing style. That's actually quite common to do in place writing instead of creating a new memory. So that's a details to note. And then once we create our custom layer norm, we can quickly test it versus vanilla torch layer norm. Sorry. And then once we do that, okay, everything is fine. Now the second the stage is to do model surgery. Basically, we are going to iteratively go through all the layer norms and replace those with our implementation, with our custom layer norm. And if we do that, we'll see we have replaced 49 layer norm operations. And then if we pass the same inputs, we create, another bot, and we pass the same inputs, we will see the same type of outputs. Now the second type of UX that Max provides is, what if you want to create your own GPU kernel with Mojo? So let's take a look at the model itself again. The example that I provided here is, let's write new GLU activation using Mojo, for example. So we provide, if you like Jupyter Notebook, we provide Mojo Jupyter Magic that you can write your own Mojo code inside a Python kernel. And here the syntax is actually, it should be quite similar to Mojo. But if you have never seen Mojo before, there are, obvious differences because it's a compile time language. All these things, for example, alias is that's compile time evaluated. We're inlining this function. There's def versus fn differences that I'm not going to go through, but the main thing is def functions are basically like Python functions. They can raise an error anytime, but fn here there's no they cannot, for example, or inside GPU kernels they can't raise. That's small details to know, but this is easy. I'm sorry. Implementation of the GLU kernel, GLU function itself, and the simple GPU kernel that I've provided here is this. Just, a few lines of code, nothing. It's quite simple. There's nothing else I wanted to show you. No major GPU features that we provide. And once you have your GPU kernel, then another thing that you need to write is basically create a custom op that can tie everything together. So, for example, you can have your own CPU implementation, you can have your own GPU implementation or XPU implementation, and then everything will be visible to the Python code. So this is the way, for example, in GPU, this is the way to launch GPU kernel with a particular grid grid size and block size. Now with that compiled and packaged, I'm sorry. Here is the easiest way that you can have to uh, load that particular Mojo package. And we are going to have our own GELU activation module here. We're going to use also use a torch.compile, and we're going to do the same type of surgery. Oops, I think I haven't. Oh yeah, I need to. I'm wondering why this hasn't been created. Please bear with me. There's some technical issue. Okay. Oh, I'm sorry. Yes, the path has changed. There is no ops here. Let me put this. For some reason, okay, it's not loading what's created. I'm gonna check. I have the package, but it's not loading it. 1 second, let me. Um, that's okay. Anyway, so I have a bit of lag. I don't know why my Jupyter isn't showing. Let me restart the kernel here. Maybe that was. Oh, sorry. Mojo P. Oh, there we go. Sorry. Yeah. Typo. That was my fault. Oh my God. It took me minutes to figure out the typo. And then once we load the packaged module, we do the same type of surgery and replace the GLU activation with our module implementation. And you see that, okay, 24 GLU have been replaced. And if I run the same input, and I should get the same outputs. Slowness is unfortunately from my side. I mean, first of all, the GPU kernel isn't really the top performing GPU kernel. It's quite slow, so that's why. Okay, we see everything to be checking out, and now the third step is if we take a look at the model itself. We are going to replace the whole GPT-2 MLP layer with MAX. And how are we going to do that is we basically implement the MLP, but here we should also know that Hugging Face is using HAN 1D, but in reality, this is just a normal feed-forward layer. And if we take a look at that implementation, and we can simplify, and also we're going to use the ops.gelu, which is provided with Max. And if we also go and create our own module, torch module, and do the same type of model surgery to replace all the MLPs, here we'll see that, okay, 24 layers have been replaced. And if I run the same inference, I should get all the same results and all these things. So, okay. Um, okay, yeah, it's working. And I think by the end, we'll see about hundreds of ops or layers have been replaced. And so with two APIs, graph op, if you want to use a graph Python API, you can get the benefit of Max, or if you want to write your own Mojo kernels and get the benefit of Mojo, there's a simple way of loading your Mojo inside your PyTorch code and get the benefit of Mojo and Max altogether. So that's the live demo that I wanted to show you. Everything that I've talked about is in Modular / workshop, and including the slides should be, I mean, the simple way to bring them up. And I mean, the last thing I wanted to show you is basically we have I've created a custom rotary positional encoding kernel that you can go and verify, and so I'm benchmarking it against torch.compile, the inductor, and on AMD, and we see that we are quite faster than torch.compile on very large sizes. This is just to show you what you can do with Max easily. So the takeaways are what I would like you to remember from this talk is basically the modular stack is quite profound. We have entirely written a new type of AI software stack that from ground up. That means from compiler to programming language to inference engine for now. But later we will have more plans to inference server and whatnot. And if you care about future proofing and no-vendor lock-in, you will get the benefit of all these things using Max and Mojo, as well as cost reduction, as well as easier operational complexity using modular package, for example. And the resources to look at are docs.modular.com. We have, of course, our source code. The majority of Mojo has been open sourced. That means standard library, all the GPU libraries, kernels, everything. The Mojo compiler itself is under heavy development, and there's a pledge that we've made. We're going to open source it by the end of 2026. If you like to learn about GPU programming in general and you have no previous experience, please do check out GPU Puzzles. That teaches you how to do GPU programming in an interactive way. And also, lastly, if you have any questions, you have any feedback, you need support, please do check out our forum as well. Thank you so much for the attention, and I'll be happy to take any questions.
Awesome. Awesome, Ehsan. Thanks, Caroline, for answering a bunch of questions as well, too. So yes, definitely check out these GPU puzzles. Those things are awesome. And I put a link in there. And I also put links into lots of stuff, specifically Chris Hodge from Modular during the hackathon gave a really good talk that I think was created by you, Ehsan, also, right? Like you
Yeah.
guys were both part of that. So that was really good because for me, it like tied together the GPU programming side of it with Mojo, and it kind of connected a bunch of dots for me. So, and these like GPU puzzles are super cool.
Exactly, exactly. I mean, the intention is to actually teach GPU programming by example, and I'm quite fond of this approach. And we get quite deep, in my opinion. I would definitely like to do and like to provide more and write more in that area. But for now, I think we have 20, yes, let's say 26 or 24 puzzles. And each is meant to teach you one specific thing. And also mention that this is quite in progress. I would like to finish it in maybe by the end of August, at least for the first edition of this book. We'll get into more advanced GPU features and also multi-GPU programming, these things.
That was actually one of my questions. As NVIDIA continues to expand, CUDA keeps expanding. I just got done. I actually submitted the final draft today to the O'Reilly folks for my book. The book that I've written is on CUDA and PyTorch and the NVIDIA GPUs. And what I realized after writing 800 pages on this topic is that I feel like Mojo, could actually reduce the size of a book like that, down heavily. But the, yeah, almost in half. But my question is, as the hardware continues to expand and get better, and tensor memory accelerator, TMA, and all these things, and thread block clusters and all that, like, does Mojo keep up with that kind of stuff?
100%, 100%,
Yeah.
yes. If you go to our API, you will see, I mean, on the Mojo side, what you'll see is basically, I mean, related to AI, we have our own MAX AI kernels. But also, if you would like to have your own versions of nothing related to our kernels, you can definitely do that. So Mojo provides everything. I mean, you can directly manipulate PTX using Mojo. That's the full power of what Mojo provides. So the Mojo itself, if I haven't mentioned it before, if you're new to Mojo, please check out the Mojo manual. But for example, if you would like to know about, let's say, I don't know if we have any PTX example here, but generally GPU GPU is a package in Mojo. I mean, that means that Mojo as a language has no knowledge of GPU. GPU is a library for us. That's quite profound to say that, but and yes, I mean, as I said, for example, all the MMAs, all the tensor ops, any new type of capability that comes up, we can easily include them in our library.
Got it. So there's always an escape hatch, I guess, is kind of what you're saying, right?
Absolutely. Yeah.
Okay. And now PyTorch has a couple thousand operations that they provide,
Yeah.
but really those break down into about 250, I think, a sort of primitive, intermediate representation called prim IR, prims IR, PrimTorch IR. So, as you continue to build out the PyTorch support, I guess, yes, asked differently. Right now, PyTorch compiler uses Triton, right? Like the OpenAI's Triton. Yeah, so not to be confused with the NVIDIA Triton inference server, which is now kind of replaced by Dynamo. Yeah, the NVIDIA Dynamo, which, yeah, not to be confused with the AWS Dynamo.
And Dynamo.
It's all confusing. But is there a thought, like, are you folks sort of leaning towards a first class like Torch compile that just replaces, right? Because Triton also does something similar where it's actually compiling down to the PTX, right?
Yeah, so I mean, there are multiple ways that I mean to answer your question, but you have also touched a lot of things. PyTorch, yes, has about I mean the full number of ops, 2,000 or so. The majority of them are for fusion, basically. So if we reduce that, yes, we'll get into 200 inside Torch, but our side in Max is actually I think around maybe 100, and I think 200 maybe is the max or so. I'm not sure, but definitely much less than 2000. And the full benefit of Graph Compiler is it automatically does all this fusion for you. And the question about Triton, yes, Triton is a capable library, but at the end of the day, it's DSL, right? So DSL has its own limitation. You don't get the full benefit of writing, let's say, CUDA or PTX directly. And if you want real performance, I mean, you cannot get from Triton. However, with Mojo, you can. So because Mojo is not a DSL, Mojo is a programming language, and you have full control on the hardware and primitives. On CPU sides, SIMD is, for example, is a native type in Mojo. Everything, I mean, all the floats, ints, everything is done in a SIMD way. And on the GPU side, is the same. So you will have access to tensor ops, tensor calls, all these things as native. So yeah, I mean, the advantages and disadvantages. I mean, of course, Mojo is new, is being developed, is not as mature as, let's say, CUDA in certain areas, but we are not just competitive, we are even better in certain areas than NVIDIA's own libraries.
And OpenAI's Triton has an auto tuning capability. Is
Mhm.
that something similar? Yeah, maybe you like mention that, but yeah, do folks support that?
Right. I think maybe about a year or years ago, we had such a thing, but I think we will plan to have a version of it inside Mojo. I'm not quite sure, but that's quite complex. I think we
Yeah.
realized that doing it properly, first we need to have Mojo and the GPU kernel programming full-fledged, and then have another layer of fusion, auto-tuning on top. But internally, yes, we are doing massive tuning and benchmarking ourselves. But I mean, as an auto tuning, no, there's no way now, but there's definitely, I mean, ways to do it in the future.
Yeah. A question came in that's actually on my list as well too. Can you talk a little bit about the tooling and the profiling for Mojo and for Max? Like, do I have, like real time, like performance counters, instruction sampling capabilities, and yeah, how do
Yes,
I actually tune this on my own?
yeah, absolutely. For debugging and for debugging, you can do CUDA GDB, the same as you use CUDA. For profiling, you can use NSYS and NSYS Compute, Nsight Compute, sorry. And yeah, all the vendor software, you can use them with Mojo as well to step and do profiling and however you do normally in CUDA as well.
And would I be able to use the PyTorch profiler? Because I know a lot of folks use that in PyTorch land.
Yeah, I mean, at the high level, so if you do it from the Python side, what you will see, I don't think you will necessarily see the max kernels. I don't think, well, I mean, first of all, I have to say that torch.compile cannot have any knowledge of max graph API inside it. It views as an opaque type of operation. So what you will see is like maybe a giant block of some sort. I haven't tried it myself, but the way I've seen it internally done is quite that. I don't think that is. We can definitely expand on it if it's required. If there is any use cases you would like us to do, definitely do reach out to us. We should be able to provide more on that. I mean, first of all, what I've showed you with the custom ops is quite new. It's been like maybe a few weeks. And
Oh, really?
yes, I mean, we are definitely refining the UX, but right now I think the UX is pretty nice. There is a graph op that you can wrap, or there is custom op library that you need to import to be able to load your Mojo kernels. These two are the only requirements.
Um, and I think you covered sort of the Python plus Mojo interoperability. Um, is it possible, like I think someone asked, can I have them both running inside of a Jupyter notebook, for example? Like I could, that shouldn't be a problem, right?
So yes, actually, so you can write Jupyter. You can write. Let me do it at the end here. You can write Mojo code using the Mojo magic here, for example.
Oh, cool.
Yeah, I mean, let's do print low. Oops. So that's it. We are also heavily investing on the UX side of it. It has some limitation, but it doesn't have the Mojo syntax highlighting, for example, if you care about
Hmm.
using the Python syntax highlighting or even LSP. But for running, I mean, simple Mojo programs or even packaging that I showed you earlier, yes, it's quite capable.
Okay, a couple more questions here. When a new model comes out, like a new architecture comes out, right? Like, let's say Llama 5. Well, actually, yeah, most recently Llama 4, right? When it switched to an MOE architecture. What what happens behind the scenes within the Mojo firewall office?
Okay, so to support that, what our team does is basically let me show you. Um, so we use Max, I mean, as I said, but we have our own components, max.nn. And I mean, similar to PyTorch .nn module, we are also heavily investing on the UX side of it. But what we do is to re-implement that model using Max. Unlike, I mean, not doing it this way, because doing it this way that I show you is actually, as I said, it's quite new, but and it should provide a bridge from existing practices. You have a PyTorch model, you want to gain performance from using Max gradually without investing completely on the rewrite. But what we do internally, we provide a rewrite of the model for you, and also for the enterprises, if this is what you're asking. And if you go, for example, to modular.com, modular GitHub, what you'll see in Max is on the pipelines, on the architecture, you can see our implementations
Hmm.
of all these famous Gen AI models, Llama 4 even, for example. And the main part is going to be on the Llama 4 or the graph side. You can see all these things. Should be similar to PyTorch API. We are also investing on making them as similar as possible with low cognitive load for folks to be able to translate this for themselves. But I mean, Llama 4 requires multiple GPU, for example. That's why you need distributed inference. Please do check out the pipelines code for a simpler model. Maybe go with MPNet as an embedding model. It has 2 layers. So you can start with that and gradually work out the complexity.
Cool. And I just reshared a bunch of links to the YouTube channel that we're going to post this recording to. Another question that was actually not on my list, but I really think it's a good question, is any plans to create like a simulation for the GPU modes for AMD and for NVIDIA, similar to Triton?
I'm not aware of it. I'm sorry, no, I don't know.
I mean, you can write Mojo code for CPU, of course, right? But and it, but yeah, okay.
Yeah, if there's any, I mean, use cases like that, please reach out. Create an issue in our GitHub or in our forum. We would love to know more about the use cases. There is no real limitation for us to not provide any of these things, and definitely is a possibility.
Yeah, I think it like comes from the same person who was asking about the tooling and sampling and things. So
Right. Yeah.
I get where they're coming from, which is they're yeah, looking for these kind of sort of development side
Yeah.
niceties. So how about supporting other chips like TPUs and yeah, whenever Meta comes out with their MTIA and all that kind of stuff?
Yeah, I think so. Right now, our focus has been on NVIDIA GPUs and AMD.
Mhm.
So we are also working on Apple Silicon as well, and this is coming up. That means all the latest M4, maybe future M5 chips, you can use MAX and Mojo with them for doing GPU programming on Metal. And this is, but there's no very complete. We are working on it. I'm not aware of any future plans for other XPUs. It depends on their vendor if they want us to collaborate with them, things like that. But I'm not aware of any other efforts for now.
Yeah, and so there's like the AWS training M chips and all that stuff as well too. But I imagine you would work out something with them and there'd be some shared development that would happen
Yes.
kind
Yeah.
of thing. Okay. And this a similar thing I assume would happen, which is you would write directly to their instruction set
Mm-hmm.
instead of writing it to some intermediate, the CUDA of training them and all that, right?
Yes, exactly. So if we go to the Mojo and I'm going to show you. So on the Mojo, on modular Mojo standard library part, you can see GPU. As I said, GPU is a library. You can see all these things.
Mm,
For example, you can go ahead and read about how we have implemented tensor cores, for example, or WAPs.
mhm.
And you can, I mean, there are different SIMD. You can see all the details that we are doing here. You can see examples of using PTX. I don't quite remember where we did that, but should be, let me see. This is for loading. Yes. Okay. So for example, this is an example of using PTX or I mean, this is perhaps a simple example of using PTX just to create an SMID. But the semantic is like you using LLVM intrinsic to call a particular PTX with its own arguments, and then you'll get what you expect from it.
Sweet. Yes, I always like seeing where the rubber meets the road here. It's like,
Exactly.
yeah, that's
Yes.
exactly like the place to go. Okay. Um, I think we've pretty much covered everything. Someone's asking about MATLAB support for Mojo.
Oh, unfortunately not. Sorry.
Not super high on the list, I assume. But okay, and all right, I think, yeah, yeah, Todd is great, by the way. Todd's like asking a lot of questions and yeah, giving a lot of comments, and yeah, he's one of my book reviewers, and I basically learned more from Todd's comments than I did from the actual research from the book, because he keeps filling me in on a lot of details here. Anything else you want to say? Yeah, Ehsan? And then
No,
I'll.
thank you so much.
Mhm.
It was great talking about all these new capabilities. I'll be happy to talk more. I mean, this is one way of approaching the whole modular stack on multiple ways, as I said, but I'll leave it for the future.
Yeah, and just to give a hint as to the timing, so like you had agreed to do this before this like custom op stuff was
Yes.
even out, right? Yeah, which I just realized. So
Yes, yes, it was quite.
yeah, thanks for not telling me that, but yeah, thanks for because yeah, that would have freaked me out. But no, yeah, I trust you guys. You guys work very quickly. What one final question was the DeepSeek week of open sourcing DeepSeek, like was that just total chaos within the modular office, trying to keep
No,
up
I
with
mean,
everything?
so it was actually, I mean, quite exciting.
Mhm.
I mean, quite the opposite from the other labs. I mean, we are not creating models. We are not in the business of that. We are empowering AI developers to write their own models inside our stack, right? So we definitely love DeepSeek. We've learned a lot from them, and we would definitely love them to use Mojo. Because they have been tuning kernels using PTX directly, and
Right.
but this is like we've been doing it for years now, and it's quite easy to do it. So please try out Mojo if you haven't.
Yeah, because I know DeepSeek uses like custom sort of PTX, or they're going directly to like
Yeah, exactly.
PTX to bypass passes and doing some special tricks. Actually, sort of interesting side note on that. There was an interview with Sam Altman, like maybe a couple months ago, where someone asked him, what did you folks learn from DeepSeek? And Sam said, yeah, I don't think they found anything that like OpenAI hasn't already implemented with NVIDIA GPUs. Like, okay, all right, Sam. so so it just kind of gives you the sense that the lab have tricks, and it just so happens DeepSeek decided to kind of release one of their tricks for these NVIDIA GPUs. And yeah, okay, great. If you have to go, go. Otherwise, I'm going to do probably 10-15 minutes, and I'm just going to kind of cover some optimizations, RL-based optimizations here. So let me get my stuff ready. And thank you so much, man. Awesome. Thanks, Caroline, as well, too, for answering questions. Figure out where I'm going to present this from. Okay, everyone, hang in there a bit while I get in here. And I'm going to share my screen. It has a whole bunch of stuff. And I think you can all see my screen. So yeah, so my name is Chris Fregly. I've been hosting this meetup for quite some time, many, many years. And we are into the AI systems performance regime of this meetup. And so last few meetups, we've been focused on this. Obviously, I've been writing this book now for, I started the research about a year ago, really just got tired of kind of not being able to piece together all the entire CUDA ecosystem and PyTorch and GPUs. And I know bits and or sort of slices of these systems, but I wanted to put everything together into one place. And so I actually learned quite a lot. My reviewers have also learned quite a lot because, yeah, like I said, this system, this space is so large, but it's really difficult when you're sifting through, X threads, Twitter threads, yeah, going through different blog posts, trying to make sense of all this stuff. So finally put it all together, got the O'Reilly folks to accept the proposal. Today, I actually just submitted the final draft. It's still in sort of a draft form. It has to get goes through all the process, and they draw the figures and everything. So this should be coming out very shortly. And thanks to all the reviewers. Todd is one of them. He's been super awesome and keeps like raising the bar here. So this talk specifically is going to be about like adaptive tuning during inference time. It's not really just inference, but that's kind of the focus. We'll be talking about reinforcement learning and some like other methods of doing this adaptive tuning for real-time systems. So why are we even focusing on this? Well, yeah, obviously inference is all the rage, rightfully so. Having faster times, to start up. And I see a couple questions here. I just want to make sure everyone can see everything. Okay, yeah. And so, yeah, like faster time to respond to end user requests makes these end users happy. We can also serve more users with the same hardware. This is the number one thing that I talk to enterprises about today, which is they've got all these use cases, but they don't have enough hardware. Cost is like, yeah, that's an issue, but they just need to serve more users with the limited GPU hardware that's available today. Yeah, and then obviously GPUs are, quite expensive, especially the latest Blackwells and the combined Grace Blackwell, which is a Grace ARM-based CPU from NVIDIA combined with the Blackwell. Yep. So that's chapters 1 or 2 and 3 and 4 talk about all the, sort of hardware level stuff in the book. Not going to get into that here at future talks. I will. I do want to reiterate this term called mechanical sympathy. This is a phrase that I have, locked in since my early Netflix days, back in 2010, where, at like places like Netflix, performance matters because you're serving at such high scale, serving, these video streams and the control plane and, trying to, yeah, like just trying to minimize the, heap size for these different servers. And so mechanical sympathy is extremely, extremely important at scale. And this is the ability to not just think about the software that you're writing, but also thinking about what's happening at the hardware level. And these are rare folks that know this entire stack up and down. And it's really the target audience for my book is people that want to understand how the software affects the hardware and vice versa. And also, I talk quite a bit about co-designing software. So, not just algorithms, but also, like different optimizations, CUDA optimizations that affect what the hardware needs to do. And, fortunately, the NVIDIA folks are talking to all these labs. They have very close relationships with OpenAI and Anthropic and all these folks. And they're, basically asking, what do you need for today's modern transformer models? Okay, like you need optimized softmax, we'll build it into the hardware, and that becomes part of the NVIDIA transformer engine is what it's called. Also, this kind of co-design affects which type of algorithms can be built. Things like flash attention, obviously, came out of this sort of co-design between software hardware. So, if you look at sort of an agent-based system with where you have like these agents, you have external tool calling, you have data stores, but there's also the sort of inference engine, and that's the part that's actually doing the reasoning, that's doing, some of the orchestration. Also, it's doing the planning to actually satisfy, what these agents are trying to do. And so that all comes down to inference. And so That's where this talk and pretty much all of my talks will be focused on going forward. Now, the book does talk about training, certainly covers training, and different optimizations there, how to do it with PyTorch and the different hardware optimizations that were built for training. But there's quite a lot of focus. I'd say 70% focus on inference, 70 to 75. So the top three things we'll be talking about today are so like dynamic system optimizations that can take a look at what's happening currently with the system, the type of load, the type of like requests that are coming in. Are these simple summarization, take a document, summarize it, which it has a very different characteristic than sort of reasoning, where you're like asking a question, a small question, but you're getting a huge reasoning chain on the output. So these are very different profiles as far as the inference engine is concerned. And so you can actually tune and change the system characteristics based on these different workloads. We'll also talk about some of the RL agents that are being used to, tune the system, to tune kernels, and to actually write better, CUDA kernels with like AI assistance as well. And so I'll talk about some really cool use cases for that. So at a very high level, there's a bunch of techniques. This is actually comes straight out of my chapter 19, which is things like changing how we use parallelism. So of course, these models, DeepSeek model is 670 billion parameters. That at best could be 670 gigs of RAM. Serving it at like FP8, you can get it down a little bit if you serve it at floating point 4. But the key is that it's still too big to fit into a single GPU. Therefore, we have to spread it across different GPUs. This is called parallelism. Based on the actual inference traffic pattern, yes, like I said, if there's short requests with like short tokens, or if there's very long requests or long inputs versus long outputs, we might want to actually change the parallelism strategy on the fly. And so these are very, very advanced and sort of research, forward-looking types of like optimizations, which is why this kind of falls in towards like the end of the book. Actually, I think it's the second or maybe third to last chapter. But these are really, really critical things, and sort of what these labs are doing like behind the scenes that, that like really give you that sort of last mile performance, that, last 1 to 2, maybe 5% performance. But these are very complex. Also, the ability to change precision on the fly. So maybe I'm doing fine at floating point 16, but I'm pretty confident that I'm generating good tokens, and my system's doing pretty well. And so based on that, I can maybe drop down to FP8 or even drop down to floating point 4-bit precision. And then I'll keep an eye on how my tokens are like, am I actually generating good tokens? If not, I might switch back to FP8, back to FP16. You probably have seen this without realizing it. You've potentially been using ChatGPT or one of the chat services, and sometimes you get really, really bad results, and sometimes you get really good results. And there's a whole lot of things that can be happening like behind these chat systems. But one thing to keep in mind is there is very likely quite a bit of this adaptive stuff happening. And sometimes you just have to rerun the same query again. And, but yeah, there's a lot of like different things that can be happening with these systems. But yeah, at scale, you have to pull out all the tricks, or else, because there just isn't enough GPU power and, things like that. So also there's concepts called chunked prefill, which lets your system do a little bit more overlap. If you're familiar with like inference, it's actually split into 2 different phases. There's what's called the prefill, and then there's decode. I'm going to talk about that a little bit on the next slide. These have very different characteristics. They use the GPU very differently because of the way that the math works out, the big matrix multiplies, and there's a lot of data memory movement and things that you're trying to minimize. And the whole goal with a separate CPU GPU configuration, where they're separate chips, is there's going to be data transfer between CPU and GPU, and the ability to hide the latency created by that CPU GPU data transfer is extremely critical. And so things like chunked prefill, you can actually chunk up prefill so that you're not spending this huge block of time doing a prefill and starving the pipeline of these smaller decode tasks that are flying through that like need to be interleaved. And so I talk about all this stuff in the book. There isn't enough time to get into it. I'll cover it over the next few months. But and then also there's concepts like speculative decoding, where we can generate multiple tokens. Typically, when you do token generation, it's one token at a time. With speculative decoding, we can generate multiple tokens. Uses what's called a draft model to sort of generate like an estimate number of 4 or 5 tokens ahead, and then the big model called the target model, that's the one that then verifies multiple tokens at once. And so there's a lot of different strategies here. There's a lot of different knobs. So yeah, basically what this comes down to is there's tons of different knobs that can be tuned, and the values of these knobs can be changed throughout the runtime, right? Like without restarting the system. There's various sort of lower level optimizations also. So down to the CUDA level, we can actually change how we're launching these, CUDA programs. They're called CUDA kernels on the GPU based on what else is actually happening on that GPU. And that's called occupancy, is, one of the things you're trying to do, which is sort of maximize the amount of, basically keeping these GPUs busy. Okay, and one of the ways to do that is what's called occupancy. And there's trade-offs. If you have too much occupancy, you're going to be using too many registers on the GPU, which then will lead to the registers having to spill over into slower memory, or and so yeah, there's just a lot of things you can do. Now, we had touched on this earlier in Ehsan's talk, but there's different ways to profile what's happening, both at the low-level CUDA kernel level, as well as the system level. So system level would be things like Grafana and Prometheus. At sort of the lower level, you want to be using tools like the NVIDIA Insight and SIGHT, and they have a whole suite, and they're starting to get better at sort of real-time monitoring and the ability to expose these things. There's also the classic NVIDIA was it SMI, command line, where you can keep an eye on things there. And of course, there's C++ APIs and Python APIs now to give you access to all of these at runtime. Okay. Another really cool trick is you can actually hot swap CUDA kernel, right, like the implementation. So, and I could do this dynamically, and I just have a little bit of like monkey patching code here on the side. If you do this with Python, yeah, you could swap it in. You have to be very careful, of course, when you're hot swapping these implementations. You have to be, concerned about threads, and make sure that you drain the whole thread pool before you swap it. Otherwise, you'll, have some inconsistent things. But these are some of the techniques that are currently either in use or being explored actively. All right. So of course, yeah, everyone loves reinforcement learning. It's the sort of holy grail of tuning systems. There's a lot of production folks that I talk to, a lot of enterprises, a lot of startups I talk to about doing this. They're mostly concerned about this kind of stuff. And of course, the concern is that these like RL systems can pick up on signals, because they're constantly exploring new and different configurations. They're constantly trying to optimize. They could potentially go down a route that is not optimal in sort of the long run. That's just part of the reinforcement learning exploration. Think of a multi-arm bandit that's trying to explore different like optimizations and then backing off, and then doing the other part, which is exploiting. So the explore exploit is key to these RL-based systems, right? And so at a very high level, we can do congestion aware routing. This is very similar to how like TCP routing, network routing works, where it's constantly keeping an eye on congestion and can work around. I mentioned there's this prefill decode phase. There's something called disaggregated prefill decode, which I have about 3 chapters on in the book, going into every detail there, where you separate these phases so that you could use either different GPUs because they're, one cluster is optimized for prefill, one cluster is optimized for the decode, and then the ability to route, to different clusters. So that's kind of higher level. Also, people have been exploring using these reinforcement learning agents to do real-time monitoring and sort of operations and, using AI assistance for this, right? So think of a classic, you are detecting, that there's high load in your mixture of experts cluster that's serving your model. You want to dynamically start to route or to like replicate these requests, or sorry, these like experts, so that you have more experts on these hotspots. And so, having this in a like reinforcement learning loop is kind of cool. The other way to do it is to just manually go in and scale out the experts that are hot, and then, or like do some sort of auto scaling. But, throwing in reinforcement learning is always fun to do, and fun and a bit scary, as these practitioners have been pointing out. There's also lower level optimizations that can happen here too. So I mentioned prefill decode. They do share data because prefill generates a bunch of KV cache that's then used by the decode. And so down to the GPU level, these streaming multiprocessors are basically the GPU cores. Think of them like cores in a CPU. And I might want to place a prefill and a decode right next to each other on the same streaming multiprocessor, 0, because they're going to share data, and that data will then only have to travel or stays on the exact same streaming multiprocessor, which shares memory and shares a lot of things, shares like registers, all that kind of stuff. So being aware of where certain prefills are currently, and then being able to then place them into place the prefill and the decode right next to each other. This is actually, what's this technique called? Pod attention, POD, right, like dash attention. There's a paper on it. This image comes right out of the paper. This does something clever where it'll assign something to the like SM, and then can dynamically change its role from prefill to decode based on where it actually lands. So it sees that, okay, I have landed on streaming multiprocessor number 1 that has currently 2 decodes and no prefills. So it's going to change the role of that task on the fly to become a prefill and then perform prefill. So, pretty cool techniques here. Okay. We're now getting towards the end here. This is some really, really cool stuff. And this is actually I think this is chapter 20. So the whole book talks about how to optimize CUDA kernels, for PyTorch, for inference, for all these things. And then I sort of follow up at the very end with this a little bit depressing ending of like, hey, by the way, all the stuff that you learned could potentially at some point actually be replaced by AI. Right now, of course, we know this isn't like totally true, but what is happening is we're starting to see signs where these CUDA kernels can actually be optimized by AI itself, which then leads to better AI, better models, faster models, and of course, more AI. So it's this sort of flywheel. So there's a few of these, starting with like Alpha Tensor, which is actually a relatively old project by now. I think it was, I don't know, 2022 or something, where Google DeepMind created, so right, like this project actually rediscovered a subquadratic GEM algorithm. GEM is general matrix multiply, so pretty much foundation of all deep learning. It on its own realized and like discovered what Strawson had discovered many years ago, which is a subquadratic complexity, time complexity way of performing a matrix multiply. So not only did it discover this on its own, but it actually discovered a CUDA kernel that was faster than the CUDA kernel that the NVIDIA folks had actually created themselves with their fleet of CUDA experts. So really cool project. Definitely check it out. I cover it in the book, of course. The other one too is NVIDIA themselves actually used DeepSeek R1, which is a reasoning model from DeepSeek, to create a optimized kernel for the attention mechanism. So the attention mechanism within transformer-based models, all the models we know of today, basically, is a very compute-heavy computation that is basically quadratic and n squared complexity, which is very expensive. And so they use DeepSeek R1, put it in a self-refining loop. They have a verifier that can verify the code and compares it against the baseline performance, to actually compute the attention. And so they use this. I think they did it for a fixed amount of time, just to time bound it. And they ultimately came up with an optimized CUDA kernel for the attention mechanism. So we're starting to see glimpses of this. There's a blog post on it out there. The other cool one here is Sakana.ai, which, if you're not familiar with them, very cool company to follow their blog. They do a lot of really, really cool research. They created this sort of AI CUDA engineer, right? So we know CUDA engineers, they're some of, I would say, the most valuable people out there, probably the most, the highest paid folks out there, because the, value proposition is real, where if you can, even reduce latency and improve performance by even 1% at huge scale, this is, millions, even billions of dollars. So they used what's called an evolutionary strategy, and they were able to create a optimized CUDA kernel that was 5 times the performance of an existing NVIDIA library with the same CUDA kernel. Excuse me. And also, I had mentioned earlier that PyTorch has about 2,000 operations in it, in total, maybe even up to 2,500 by now. But it really breaks down into about 250 primitive operations that all the other ones are really built on. And Sakana's CUDA engineer, AI CUDA engineer, was able to actually process and understand about 230 of these 250 primitive PyTorch operations. So pretty cool stuff. I will warn you, these take a pretty tremendous amount of compute power. So if you're starting to think, oh, I could build a startup that'll do this, this is very, very expensive stuff. You are going to require a whole lot of capital, and it's still in the very early phases. But we're seeing performance that is actually very reasonable. And okay, so final thoughts here. Start to consider and start to embrace these sort of reinforcement learning ways of optimizing, and also really don't be afraid of the AI assistants. Yeah, we all know this is very likely going to replace some of the lower level, some of the tedious parts of our jobs, but it really lets us focus on higher level system optimizations, and so don't be afraid of these things. The end goal is, of course, better user experience, serving more users with the same hardware, which can save us quite a bit of money. So thank you much. Let me look at the questions. I don't have a whole lot of time because I do have to jump here in a bit, but let me actually grab the quest or the links, all the links. So let me put that in before folks drop. So the book is down there. All the modular stuff is up at the top as well. The YouTube video for this will be posted in the link. I'll repost it here for that. And let me go back to here and let me look at the questions real quick. All right. So yeah, the book should be released here in the next month or two. Yeah, it's about 800 pages. Actually, little tip there. I think it's up to almost 900 based on what I submitted yesterday. So I think the O'Reilly folks want me to try to make it smaller, but you know, you folks are, and I mean, I do this too. I spend a lot of money on these books, and with that, I certainly want a lot of content, and that's definitely what I'm hoping for here. Yeah. Okay. So I think the recording will be posted later today as soon as it finishes encoding. Okay. Let's see. Okay. Yeah, so I think we're good. Got a lot of cool. So oh, and then yeah, I think so. Yeah, someone's asking a question that I probably skipped over here, but things like adaptive parallelism and dynamic precision changing, these things are tricky, and they do require, especially if you're, for like the like KV cache, for example, if you're making changes to precision and or even parallelism, the KV cache has to be updated, and but there are ways where if you're changing, let's say you're changing the degree of your tensor parallelism, and so let's say on the prefill side you are using tensor parallel, so you're splitting up the model across 4 different GPUs because it's so big that it won't even fit into a single one. Now, on the decode side, you are using bigger GPUs, like larger ones that have more memory. So let's say you only need tensor parallel 2. Because you're able to split prefill and decode into their separate clusters and can use heterogeneous GPUs, you may need to do the adapting, between the prefill cluster and the decode cluster, and same with the precision. And so what you do there is basically have a transformer, or sorry, I shouldn't use the word transformer. You have code that can perform a transformation to from the KV cache data that's being sent from the 4 GPU tensor parallel to the 2 GPU tensor parallel cluster, and it'll basically reshard on the fly. And then so there's some drawbacks there because there is a little bit of extra time. The hardware providers, right, like NVIDIA, they certainly know about this. They have built in, compression, decompression engines, for example, that's into the hardware. I would expect them to also do something similar for, changing parallelism and, different optimizations there. So that's basically what these hardware providers keep doing, is they're looking at the algorithms that the labs, that the researchers are creating, that they're seeing what's actually popular, what's actually making real gains, and then the hardware provider that next year or the generation after have then built it into the hardware to speed things up. So that's my favorite part about like writing this book, was seeing all of this co-design come together. You'll hear the term co-design come up quite a bit, similar to mechanical sympathy, where you want to co-design the like GPU hardware, the CUDA kernel, PyTorch algorithms, and all that good stuff. So yeah, thanks everyone. Let me see, anything else? Yeah, and Todd, special thanks to you. I'm going to definitely give you a shout out in the book for all the great feedback that you've given on the book. So next month, I can't remember what we're actually talking about next month. I think we've got someone either from Base 10 who are experts in inference, talking about high performance inference. optimizations. And then there's another one coming up from the vLLM folks. They'll be talking about some of the hardest problems that they've had to like implement within vLLM, things like chunked prefill, different strategies there. Obviously, KV cache transfers. We'll be talking about the newer Nixel NIXL transport layer that came out of NVIDIA and was released along the NVIDIA Dynamo project. In the next couple of months, I'll hopefully have someone from the NVIDIA Dynamo project on here. Kind of waiting for a couple more features to land within Dynamo and then have them explain, all of those different things. Dynamo is still relatively early in it's very powerful, but it still needs a few more features to be peak performance. So thanks everyone. I'll post this very soon.